This video is mostly about graphing polynomial and irrational functions, but in the first problem we look at a domination question of a polynomial, a power function in fact, compared to an exponential growth function. Which function dominates, grows faster, as x goes to plus infinity? It is something you should just know, but we do want to provide graphical evidence for the answer. So we've got a polynomial 10 times x cubed, and we have an exponential growth e to the 0.5x. The thing you really should just know is that exponential functions dominate as x goes to plus infinity compared to the polynomial, or in this case just a simple power function. No matter how big that power is, no matter how big this coefficient is, no matter how small this positive coefficient of x is, the exponential function will dominate. As far as providing graphical evidence, it's not a proof. We do want to make some window where we see ultimately this exponential growth function growing faster than the polynomial growth. If we pick a typical kind of window, I picked from 0 to 10 in the x direction and the y direction, we may not see that. Okay, let's go ahead and plug these functions in. We have 10 times x cubed right there, and then we have the second function is e to the 0.5x. All right, let's just see what happens on this particular window. 10x cubed gets graphed first. It's growing very, very rapidly. E to the 0.5x gets graphed second. You can see it's growing rapidly too, but it seems like not as fast. But we know this has got to be the answer. E to the 0.5x has got to catch up to the 10 times x cubed graph if you make your window large enough. Now maybe we just didn't go large enough in the y direction. Let's try going up to say 1,000 here and make our y scale be 100. There's 10x cubed, and here is, well, you can barely see it, e to the 0.5x. It looks like it's not catching up. Okay, so we need to go further in the x direction as well. Let's try going out to say 30 here, and let's try letting the y max go to maybe even 1,000,000 or something. Let's see, there's 1,000,000 right there. Let's see what happens. Let's make this 100,000. So let's see, that's the first graph, and here's the second graph, and there we see it. That's the exponential growth function. We went out to x equals 30 there. It looks like finally the exponential growth function catches up when x is in the 20s somewhere. You could use the trace feature to try to figure out where. Maybe we should go ahead and do that. Let's see if we can approximate where. We could also use the intersect feature. It's somewhere around x is 23 or 24 or so where they cross. We could use the intersection feature to figure it out more precisely. In the second problem, we are given a graph, and we ultimately want to find a polynomial with that graph. We start with some other questions. Part A, what is the minimum degree of a polynomial with the graph that you see right here? The first thing to do is to look at the number of x-intercepts, also called roots or zeros of the polynomial. We see that there are 1, 2, 3 of them. Based on that, you'd say the minimum degree has to be at least 3, but that's not necessarily the final answer. And if you think about it, based on the end behavior, it can't be the final answer. Another thing that we can look at is the number of so-called turning points of the graph, where the graph changes from increasing to decreasing, like right there, or decreasing to increasing, like right there. We see that there are 1, 2, 3 turning points. Add 1 to that number, and that says the minimum degree has to be 4. Okay, this is factual information to know based on polynomial graphs. So the answer for part A is 4. That's the minimum degree. It could be higher degree, like 6 or 8 or 10. Notice I only said even numbers there, but that's the minimum degree. And as far as finding one answer for the polynomial with this graph, that's going to be good enough. Part B, is the leading coefficient of the polynomial positive or negative? The fact that ultimately for part E, the end behavior of this polynomial is downwards, y goes to minus infinity as x goes to plus or minus infinity, says that the leading coefficient of the highest power of x has to be negative. So the answer here is negative. B is negative. Part C, find a possible factored formula for a polynomial with this graph. So we're trying to write the polynomial first in factored form, okay? That is definitely easier than trying to write it in the standard form right away. Okay, we'll have to actually do some multiplications to write it into standard form, okay? So what do? We again look at the x-intercepts. Again, there are 3 of them, right there, there, and there. And it looks like, based on what we're given, they are at particularly nice numbers. That always makes these kind of problems easier. -2, 1, and 3. So you could initially think, well, maybe it's x plus 2, because x plus 2 has -2 as a root, times x minus 1 times x minus 3, but that would be trouble because that would only be a cubic. Notice that the x-intercept at 1 is a root where the graph just bounces off the x-axis, you might say. That's indicative of something called a double root, or a root of multiplicity 2. And what that means is the factor x plus 1 should really have a square. Okay, it should be to the 2nd power. We don't know what the coefficient in front of all this is. We don't know what the leading coefficient is, other than to say it's negative. But the fact that the y-intercept looks to be at 12 will help us find that leading coefficient. So in part C, what we're going to do is we're going to write f of x, this polynomial, in factored form with a leading coefficient. We'll just call it a in front. A times x plus 2 is one factor, because -2 is a root. X minus 3 is another factor, because +3 is a root. And x minus 1 quantity squared needs to be in there as well, again, because 1 is a double root, again, also called a root of multiplicity 2. Actually, we could figure out the a right away here, because we know f of 0 is going to be 12. 12 equals f of 0 will allow us to solve for a. A times, when we plug in x equals 0, we'll get 2 and a -3 and -1 squared. So this becomes, it looks like -6a equals 12. We can easily solve that for a by dividing both sides by -6 to say that a is 12 over -6, which is -2. And the final answer for the factored form of f of x is -2 times x plus 2 times x minus 3 times x minus 1 quantity squared. By the way, the order of these factors doesn't matter. There we have it. That's the answer for part C, a possible factored form of a polynomial with this graph. There are other answers, again, if you wanted to do higher degree polynomials. However, that does make things trickier as far as the way these x-intercepts would look. For example, if you did an x minus 3 to the 3rd power or something, it actually does make the x-intercept, the way the graph crosses the x-axis, look a little different. So this is going to be the best answer, really. All right, part D, expand the factored polynomial from part C into standard form, where you have the expressions to various powers being added up and not factored like this. Okay, so that's just some algebra. We need to do some foiling, for example, of x plus 2 times x minus 3 and x minus 1 quantity squared, but then we'll have to go beyond that. Just keep the -2 out in front. If I FOIL this, right, FOIL first times first, outside times outside, inside times inside, and last times last. First times first is x is x squared. Outside times outside is -3x. Inside times inside is +2x. -3x plus 2x is -x. Last times last is 2 times -3 is -6. And if I square x minus 1, imagine multiplying it by itself. First times first is x squared. Outside times outside and inside times inside are both going to be -x, so I'll get -2x. And then last times last is going to be -1 times -1 is +1. All right, we need to keep going, but I can't use FOIL anymore because these two expressions are both trinomials instead of binomials. But it still can be done. Here's the way I do it. Go to the first factor here and its first term, x squared. Multiply it times every term over here. Ultimately, this is all based on the distributive law. X squared times x squared is x to the 4th. X squared times -2x is -2x cubed. Hopefully I don't make a mistake. X squared times 1 is x squared. All right, so I took x squared and multiplied it times every term. Now go to the next term on the left, -x, and multiply it times every term on the right. And for sake of ease of combining like terms, I will put like powers underneath each other. So I have -x times x squared is -x cubed. And then -x times -2x is +2x squared. -x times 1 is -x. Last, go to the negative 6 there and multiply it times every term. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2x is positive 12x. And negative 6 times 1 is negative 6. Now combine the like terms and you'll have your final answer after you also multiply through by negative 2. X to the fourth minus 3x cubed. Looks like we have a 1 plus 2 minus 6 is negative 3x squared. Negative x plus 12x is plus 11x, and then minus 6. Now distribute the negative 2 through. The final answer is negative 2x to the fourth plus 6x cubed plus 6x squared minus 22x plus 12. There is the standard form of this polynomial. It's much harder to go the other way, right? If you got the standard form, it's much harder to factor it. You need something called the rational roots theorem to help you do it if you don't have much technology, or you need some guessing and hope that you're lucky. Part E, what is the end behavior of the polynomial as x goes to plus or minus infinity? I actually already said that. You can say, because the graph goes down forever and ever, you could say y goes to minus infinity as x goes to plus or minus infinity. You could also write it with limit notation. You could say the limit of this function as x goes to plus or minus infinity is minus infinity. Okay, that's just shorthand notation to say that the graph goes down forever and ever below any horizontal line as x gets big either positively or negatively. I can get below any horizontal line. In the second problem, we were given a graph and we wanted to find a polynomial. Here in the third problem, we're given a polynomial and we want to make a graph. We're also given a rational function and we want to make a graph. This is a cubic polynomial. F of x equals x cubed minus 2x squared minus x plus 2. And the goal is to graph it here without technology. Yikes. Can that be done? Yes, people did it before they had technology, okay? Let's go ahead and start with this. It is helpful to know something called the rational root theorem that helps you guess possible rational root, and then you're just kind of crossing your fingers and hoping your teacher gives you a polynomial with rational roots that are fractions or maybe even integers, whole numbers, plus or minus 1, plus or minus 2, etc. You're hoping those are the roots so that you can factor this more easily. The rational root theorem would say that if a rational number p over q, where p and q are whole numbers, positive or negative, integers they're called, will be, if it is a root, then p must be a factor of the constant term 2, meaning p must be plus or minus 1 or plus or minus 2, and q must be a factor of the leading coefficient, which in this case is a 1 because you don't see anything right there. It's assumed that that's a 1 in front of there. So the possible rational roots are actually integers here, plus or minus 1 or plus or minus 2, and you're just kind of hoping that those are roots. Now, there is a quick way to figure out whether those are roots called synthetic division. I want to instead show you long division, which is a little longer. That's why it's called long division, to help you guess possible roots, because that's going to apply more generally when you're not just dividing by linear polynomials. Actually, we can pretty quickly guess a root. For example, 1 is a root. If you plug in x equals 1 here, you get 1 minus 2 minus 1 plus 2 is 0, right? You're going to get 3 plus negative 3 is 0. So 1 is a root. X minus 1 should be a factor. And when you do synthetic division, you do something similar to this, except you don't put the x terms in, and you'd actually put a 1 instead of an x minus 1 here. If you don't know synthetic division, don't worry about it. I'm doing long division. I'm dividing x minus 1 into the polynomial here, you might say. So I have to ask, what do I multiply the highest power here, x, to get the highest power there? I've got to multiply it by x squared. Okay, x times x squared is x cubed. Now go ahead and take x squared and multiply it times each term and put the answer down there. X squared times x is x cubed. X squared times negative 1 is negative x squared. Then you subtract. With synthetic division, you add. That's another difference. Again, don't worry about it if you don't know it. Negative 2x squared minus negative x squared is the same as negative x squared plus x squared. Okay, that's going to give you, careful, negative x squared there. Okay, if you want to double check here, if you add these two expressions, you're going to get that. -1 plus -1 is -2. Bring down the other things, it's like you're subtracting 0, like that. Now ask, what do I multiply x by to get -x squared? It'll be a -x. Multiply it times each term and put the answers down here. -x times x is -x squared. -x times -1 is positive x. Subtract, get cancellation. -x minus x is -2x. This 2 comes down. Now you got to multiply x by -2 to get -2x. We get a -2. We should get a remainder of 0. Multiply -2 times each term, you get -2x. -2 times -1 is +2. We get a remainder of 0. That's what we wanted. That's telling us x minus 1 is indeed a factor. And what's we're left with, that's the quotient up there. That's a quadratic, which hopefully we can factor just by thinking about it. And in fact, you can. If you think about factoring this with a little bit of practice, you realize it factors as x plus 1 times x minus 2. You could try to check it by foiling here. X times x is x squared. -2x plus x is -x. And then last times last, 1 times -2 is -2. This is a factorization of our cubic based on factoring this quadratic there. So the x-intercepts are 1, -1, and 2. It's a cubic with a leading coefficient that's positive. The end behavior is that y goes to plus infinity as x goes to plus infinity, and y goes to minus infinity as x goes to minus infinity. With these roots, we could also figure out the y-intercept. F of 0, plug in 0 here is 2. So we can make a pretty decent graph pretty quickly. Roots at -1, +1, and +2. And a y-intercept at 2. Thinking about the end behavior, the graph is going to look something like this. Okay, and you could try to make it more accurate by making the scale more carefully, and maybe you make a bigger scale and you plot more points and that kind of thing. But that's the basic graph of this function. And we can draw arrows to emphasize the end behavior if we like. On to part B. G of x is 2 times the f of x that we just did in part A, divided by this cubic that you see right there. The goal is to graph g of x without technology as well. Make sure to identify any vertical and horizontal asymptotes of g of x. Okay? So, first thing to do is write g, the numerator and denominator, in factored form. The denominator is already in factored form. The numerator, well, up here it's not in factored form, but down here it is. So write g of x in factored form based on what we did in part A. And notice the 2 there. I purposely put a 2 there. So we're going to have a 2 in front times f of x in factored form, like this. And the bottom of g of x, looking up here again, is x minus 1 times x plus 2 times x minus 3. X minus 1 times x plus 2 times x minus 3. Now the initial thought here is, oh, g of x is going to have roots where the top has roots and vertical asymptotes where the bottom is 0. But that's wrong. Okay? It's almost right, but it's not quite right. You need to cancel any common factors that you see. And in g of x, in the top and the bottom, there's a factor of x minus 1. Those need to be canceled to get this right. Okay? They are part of the formula of g technically, but you want to get rid of them to help you correctly identify roots and asymptotes. So this simplifies g to being like this. There were no other common factors that can be canceled. And now once you've canceled common factors, now you can say the x-intercepts of g are going to be at the roots of the numerator, and the vertical asymptotes of g are going to be at the roots of the denominator. You can also say right away, without making a graph yet, that g of x does have horizontal asymptotes. The degree of the top and bottom in both cases is the same. Degree 3 here, degree 2 here. That means there is going to be a horizontal asymptote. And in fact, the horizontal asymptote is a horizontal line, y equals some constant, that the graph approaches as x goes to plus or minus infinity And the value of that constant turns out to be the leading coefficient of the top divided by the leading coefficient of the bottom. 2 divided by 1, 2. The line y equals 2 is going to be where your horizontal asymptote is. Okay, let's also find the y-intercept of g for good measure, g of 0. Plug in 0 here, you'll get 2 times 1 times negative 2. Plugging 0 there. Divided by 2 times negative 3. Looks like the y-intercept is at positive 2/3. All right. So let's go ahead and make a graph. And after making the graph, we'll also answer part C, which asks what is the limit as x goes to plus or minus infinity of g of x. In fact, we've already answered it. It's 2. That's the horizontal asymptote. So B and C here. We are not really finished with B. This part B was to also make the graphs. But let's go ahead and make the graph here. Horizontal asymptotes at y equals 2. Let's say that's right here. I'll make a dashed horizontal line there. That's going to be your horizontal asymptote. X-intercepts at -1 and positive 2. Say -1 is right here and positive 2 is right here. Y-intercept at 2/3, right about there. Vertical asymptotes at -2 and positive 3. So here's -2. There's a vertical asymptote for the function there, and positive 3, a vertical asymptote for the function right there. You could plot some points to help you figure out what's going on here. It looks like in the middle here, probably the graph's got to be doing something like this, right? In there, if you're going to connect those 3 dots, and the rational function will be continuous wherever it doesn't have vertical asymptotes. Polynomial functions are continuous everywhere. And because of that, there are no more x-intercepts here. It's got to go down forever and ever here and here. We could plot points bigger than 3 and less than -2 to see what the function values are. Are they positive or negative, for example? For example, if you plot the point where x equals 4, let's just think about whether it's positive or negative. That's positive, that's positive, that's positive. Everything's positive when x is 4. The function's got to be positive. There's no x-intercepts here. It's got to be coming down from infinity, you might say, like that when x is bigger than 4, because there's no other x-intercepts besides at -1 and positive 2. If you plug in a number less than -2, like -3, again, there is no x-intercepts. And this is a horizontal asymptote. The function's got to be doing the same kind of thing over here as well. If you want to just double check, imagine plugging in -3. We'd have a positive number times a negative number times a negative. That's positive. Negative times negative is positive. Divided by a negative number times another negative. Again, the product of 2 negative numbers is positive. It is positive, confirming things. You'd have something like this. A little extra confirmation, you could think about what happens to this function as x approaches 3 from the right or 3 from the left. The function approaches positive infinity if x approaches 3 from the right. I'll let you think about that. And negative infinity as x approaches 3 from the left. You can also think about the same kind of thing as x approaches -2 from the left or right. And again, finally, the limit as x goes to plus or minus infinity of this function, this rational function g of x, is the value of the horizontal asymptote, which is 2. In our last problem, we are given a rational function, and we want to first find its so-called slant asymptote, and then we want to graph this function and its slant asymptote. What is a slant asymptote? That's a slanted line, not a horizontal line, but a slanted line with a positive slope or a negative slope that the graph approaches as x goes to plus or minus infinity. And a rational function will have a slant asymptote exactly when the degree of the top is 1 more than the degree of the bottom. Here you see the degree of the top is 2, that's the highest power of the x, and the degree of the bottom is 1, the highest power of x down there. 2 is 1 more than 1. This has a slant asymptote, right? How do you find the slant asymptote? You want to do long division in general. So we have x plus 2 being divided into x squared minus 5x plus 4. This time, we won't get a 0 remainder. In fact, to emphasize that, we could factor the top. The top factors as x minus 4 times x minus 1. There's no common factor there. X plus 2 does not divide into x squared minus 5x plus 4. And that means we are going to get a non-zero remainder, and that's okay. That's what happens here. What is the quotient? Well, start it off, we need to multiply x by x to get x squared, so put an x up there. X times x, excuse me, x times x is x squared. X times 2 is plus 2x. Subtract. Negative 5x minus 2x is negative 7x. Bring down the 4. I need to multiply x by negative 7 to get negative 7x, so I get a minus 7. Then I get negative 7x. Negative 7 times 2 is minus 14. Subtract 4 minus negative 14 is positive 18. And that is a quantity whose degree, its constant, is 0, which is less than the degree of this. We can stop here. That is the remainder. It's not 0. Emphasizing again that x plus 2 is not a factor of the numerator. Negative 2 is not a root of the numerator. And this thing up here is the quotient. And it turns out that the quotient in this kind of setting is the slant asymptote. Why? Let's explain why. The fact that we got this as the quotient and this is the remainder means that we can write this rational function as the quotient, x minus 7, plus the remainder over the original thing we were dividing by, 18 over x plus 2. If you don't believe it, you don't believe that this is what we can do, let's call this quotient q of x and the remainder r of x, even though it's a constant. That's the quotient, and that's the remainder. Why does this work? It's called the division algorithm, but if you want to just check it, go ahead and combine these by getting a common denominator of x plus 2. It's just checking the algebra here. Get a common denominator, I have to multiply this x minus 7 by x plus 2 and then divide it by x plus 2. So I'll get x minus 7 times x plus 2. This fraction already has that common denominator and has an 18 on the top. Now go ahead and multiply the top out, FOIL that. I will get this. And then when you simplify, you get the original function, x squared minus 5x plus 4 over x plus 2, matching what you see right there. Okay, so that's just a check that this is correct. Coming back to the reason why x minus 7, the quotient, is the slant asymptote, think about what happens to this function as x goes to plus or minus infinity. As x goes to plus or minus infinity, this fraction that you see here goes to 0, gets very, very small, as x gets very, very large. In fact, it gets arbitrarily small is the more official way to say it, as x gets arbitrarily large. I can make it as close to 0 as I like by making x big enough in either the positive or negative direction, which means this function, h of x, acts like its quotient, q of x. Their values are very, very close together when x is very, very large, and that means their graphs are close together, and that's why it's a slanted asymptote, and this graph is slanted with a slope of 1. All right, so that's the slant asymptote. Part B, we want to actually graph h of x and its slant asymptote. That's fairly easy. We also have h of x in factored form on the top and the bottom and nothing canceled. The x-intercept of h are going to be 1 and 4, and the vertical asymptote is going to be at -2. And I want to draw the slant asymptote in there as well. So let's quickly make a graph. Again, the x-intercepts are at 1 and 4, right about here and here. The vertical asymptote was at -2. Let's be right about there. There's a vertical asymptote. The slant asymptote is again the function x minus 7. So that's going to be aligned with a slope of 1 and a y-intercept of -7. Let's say -7's down here and +7's right about here. So the slant asymptote, which I'll draw as a dashed line, looks about like this. I can also do things like find h of 0. H of 0, if you plug in 0, you can see you'll get 4 over 2 is 2. 4 over 2 is 2. That's the y-intercept at 2. Yeah, and these are the only x-intercepts. The graph's got to be positive here. It's got to have this vertical asymptote. It's got to come down from plus infinity, you might say, about like this. I'm doing what my students do and graph it a little too fast. Let's ignore that part. Something about like this. It's got to go negative here. Then back to positive, and ultimately approach that slant asymptote. I'm going kind of fast. I'm not drawing it as nicely as I should. What about when x is less than -2? It's got to be negative in value. There's no other x-intercepts here. It can't come down like that. There is still this vertical asymptote here. Without plugging in points, it's got to do something about like this over here. Okay? To try to get it more accurate, you'd want to use your technology, but this is approximately a rough graph. Thanks for watching.